Okay, well, we have a lot to do today. So what we're going to learn today is how to prove the correctness of the do statement. So the first thing we're going to look at is P.28. Okay, so here P.28 is the do statement. It's do, and it's a guarded. Notice that it has a guarded command in it. But instead of having an if and a fee, it has a do and an od, do and odd, or ode. I don't know how to pronounce that. But anyway. And so now it's possible in the guarded command language to have more than one guard in a do statement, but we won't ever have occasion to use that particular feature. So for us, we're going to just analyze what happens with the do statement when we have the guard like this. And as an example, I want to start off by first doing an example, just to show you how the do loop works. Okay, so here's example. Okay, and here's the program. xi gets 0, 0, and then do, and we're going to have I less than 4. That's the guard. So if I is less than 4, we're going to have I comma x gets I plus 1 comma x plus I, and then into the do odd, right? So everybody understands in this particular, so comparing this with P.28, everyone understands that in this statement, I less than 4 is the guard. So this is the guard B, and this is the statement S. Are you with me? Yeah? Okay. So now, in order to sort of show how this works, what I would like to do is go through, and I want to do a trace and show you, and then ask a question. So let's draw what we're going to call a trace table. And so here, in the first column, we're going to have the guard, which is I is less than 4. Now, I'm going to leave some space here on this side of the trace table, and we're going to come back and fill it in a minute. And then we're going to trace the value of I, and we're going to trace the value of x. All right? And as we go through here, so let's just trace through. I'll explain how this do statement works, and we'll go through and let's see how this do statement works. So the value of the guard I less than 4, we start off with some unknown value. We'll start off with some unknown value for I, and we'll start off for some unknown value of x, right? Are you with me? Okay, so what happens here is the first thing that happens in this program is this statement executes, right? This x comma I gets 0, 0. Are you with me? So what that causes to happen is I gets 0 and x gets 0. Is everybody clear on that? And then the semicolon is a sequence. So after this statement comes the do statement. Now the way the do statement works is this. It's a repetitive statement. So what happens is when you enter the do, you check the guard. If the guard is true, this statement executes, and you check the guard again. And you keep doing that over and over and over again. You do it. So you do, as long as this, so you check the guard if it's true. If this guard, if you ever go back and do it again, and if this guard is ever false, then you quit the loop. And if there's another statement after that, you execute that statement. Otherwise, you're done with your program. Okay, so does everybody see that's how the do statement works? It's a repetitive statement. All right, so now we did this 0. So now, okay, so you tell me. I is less than 4. 0 is less than 4, true or false? Yep, it is true. So therefore, what do? I comma x gets I plus 1 comma x plus I. So here, for this test here, we'll put true on this line, okay? And because this is true, then on the next line, we'll put what I and x get. So what happens if you do I gets I plus 1, x gets x plus y? What's the value of I and what's the value of x? 1 and? 0. Yeah, okay. Are we good? Okay, and then we go back and test the guard. 1 is less than 4, true or false? So let's put true here for the value of the guard. And then if we do this statement again, what happens? What do we get? So we get 2, 1. We test the guard what? True. What happens here? Up. 3, 3. Is everybody following this? 3, 3. Okay. And then what happens with the guard? True. Then what is it? 4 and 6 is correct. And then what happens to the guard? False. And now because the guard is false, then what happens is we terminate. So false, we terminate. All right? Now, tell me, what does the loop do? What is the loop calculating? I mean, I just goes up by 1 each time. But what about x? What is it actually? What does the loop set x to? The loop, let's just state it. The loop sets x to what? To what values? Well, I mean, obviously it's 6, but where did the 6 come from? What did we add? What? Yeah, exactly. So the loop sets x to 0 plus 1 plus 2 plus 3. That's what it sets it equal to. Now tell me, how would you quantify this? How would you quantify this? In other words, what it does, it sets x equal to what? How would you quantify this? How would you write this to write this as a quantified expression? How would you write that? Yeah, sum. Sum. Now, sum over what? Some dummy variable, right? So let's just say, let's call it k. Now, range what? Range what? 0 to 3. Yeah, 0 less than or equal to k. Yeah, but let's say less than 4. Huh? Look familiar up here? Less than 4. Body what? Body what? Huh? K. Yeah, body k. All right? Are we good? Okay, so now here's my question. My question is, now comes a very important question. My question is a question about an invariant. What is the invariant of this statement? This statement, ix, I plus 1, I comma x gets I plus 1 comma x plus I. So here, let's write that down. Question, what is the invariant? What is the invariant of the statement I comma x gets I plus 1 comma x plus I plus 1 comma x plus I. What is the invariant of that statement? Now, what do we mean by an invariant? Can you tell me what an invariant is? What's an invariant?
I don't think they can.
What's an invariant? Do you remember what an invariant is?
Something's the same.
In both the what? Precondition and the postcondition. Okay, that is, and the postcondition, correct. So, that is, what is P in the following? P I comma x gets x, sorry, I comma x gets I plus 1 comma x plus I, postcondition P, same P, right? What is the invariant? Can you tell me what the invariant is here? In other words, what can I write down here that's true regardless of whether if I do this, it's going to still be true. Actually, that's a good point. I is less than 4. You know, that is an invariant. That's a good answer. The thing of it is that there are many invariants. I mean, you know, we could say true. We could say I is less than 4. We could say I is less than 10. We could say X is less than 1,000. I mean, you know, there's lots of invariants. You're right. But there is a, so when you ask, what is the invariant? The question is, what is the most important invariant, or the invariant that is the most useful? It might be kind of hard to come. What is true? I mean, what is true about the what is true about the value of x? What is true about the value of x both before and after? Both before and after. What is true about the value of x? See, what did x start off to be? X started off to be 0. Okay, so we added 0 to it. It's 0. Then it was 1. Then it was 3. Then it was 6. And each time we went through this, we did something to this. You know, we executed this. But what was true both before and after? Every time we did this, what was always true? Regardless of where we were here. What was x equal to? Anybody know? Oh, we have a little silence in the peanut gallery here. What is x equal to? You know, regardless of whether it's the first time through, the second time through, the third time through, what is true at the beginning, and then after we execute, it's the same at the end. It's the sum on what? K, range what? 0 less than or equal to k less than what? No? I. See, I is changing, right? But still, less than I, body what? Body k. This is the invariant. All right? Now, how can we check to verify that this is the invariant? Check by, how do we check to see how can we do a computation to show that this is invariant? Check by proving what? Let's call this P. We're saying this is P. Here, let me stick this in here. P colon. This whole thing is P. So how would we prove that this is an invariant? What would we do? What would we have to prove? Check by proving what? By proving, oh, well, here it is. We check by proving this, right? Now, how do we prove? How do we show that this is true? If this is what we're claiming P is, what do? We have to show that what? That P implies good. P implies what? Precondition of this dot P, exactly. So let's compute it. And we'll assume the conjuncts of the antecedent, right? So let's do WP. So what would that be? WP dot what? I comma x gets I plus 1 comma x plus I dot P, right? So this equals by, now what's our P18 and exactly. P18 and textual substitution. So what will this be? Let me see. It's this, only everywhere there's an I, we put a what? I plus 1. And everywhere there's an x, we put a what? X plus I. So what will this be? X plus I equals sum on k. Everywhere there's a I, we do I plus 1, right? So this is what? 0 less than or equal to k less than what? I plus 1 body k. All right? But this equals by, everybody knows now. Exactly, split off term. See how split off term comes up all the time? And now what's the last term here? It's I, right? Because this is less than I plus 1. So the last term is I. So k, and this is sum, right? So it's plus I. So it's going to be x plus I equals sum on k, 0 less than or equal to k less than I, body. So now this is going to be I, right? And then the term that was split off was plus I. But now this equals by what?
I mean,
Assume conjunct x equals this, right? So here we can put x, right? So here we assume conjunct P. Assume conjunct P. And if we assume conjunct P, this is x plus I equals, and this whole thing is x. X plus I. And sure enough, this is what? True, right? Equals by, what is it? I forget. What's the number? Reflexivity. I mean, I think this is reflex, right? X equals x, that's reflexivity. We'll just put we know that equals is reflexive, so okay. All right? So that shows that that's the invariant. Okay, so now look. Now let's go back to here. You see, this now, if we, now, let's do, here's our, now that we know what the invariant is, let's actually compute the invariant. Here, so what did we say the invariant was? It's x equals the sum on k equals the sum on k, 0 less than or equal to k, less than I, body k, right? Now let's actually compute this invariant and see if in fact it is true. At this particular point, what is the value of I and what is the value of x? 0 and 0, right? So this evaluates to what? 0 equals sum on k, 0 less than or equal to k less than 0 body k. Well, is this true? Is it true? What do we have here for the range? Empty range. What's the value of the empty range? For addition, it's the what?
Zero.
The identity, right. It's the identity, so that's 0. So 0 equals, yeah, that's true. What about at this point? What do we have here? This says what? This says 0, x is 0, right? This says 0 equals sum on k, 0 less than or equal to k less than 1 body k. Is that true?
Yeah.
That's true, right? Because it's 0. There's only 1, right? So it's the 1-point rule.
Yeah.
So that's, okay. So the empty range rule, 1 point. And what about this? What is this? This says 1 equals sum on k, 0 less than or equal to k less than 2 body k. Well, is that true? Yeah. And here this says 3 equals sum on k, 0 less than or equal to k less than 3 body k. That's true. And this says 6 equals the sum on k, 0 less than or equal to k less than 4 body k. So that's true. So true, true, true. True, 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 true. It's invariant. Yeah? It's true both before and after. Okay? So that's the concept of this is the concept of a loop invariant. Now, in order to prove that a loop is correct, I already have it up here. There's a checklist on the next slide, but before we go to the next slide, I want to discuss a little bit what is called the fundamental invariance theorem. This is P.29, and make a few comments about that. Okay, so let's take a look at it. Now, you understand that P.28 tells us what do is, right? It's an abbreviation for do. Now P.29 is the fundamental invariance theorem, and it says, suppose P and B, S, P holds. That's a Hoare triple. That is, execution begun in a state in which P and B are true terminates with P true. right? So that's just the interpretation of the Hoare triple that he's saying there. So suppose we have that Hoare triple, P and B, S, P. And also, suppose that we have the following Hoare triple, P, do, B, arrow S, in do, guard B, if B, then statement S, in do, true. That is, execution of the loop begun at a state in which P is true terminates. Then the conclusion is we have P and then do, B arrow S, in do, and then the conclusion is P and not B must be true. Now what in the world is going on here? What is this fundamental invariance theorem telling us? So this is B point 29. Fundamental invariance theorem. Well, look, there's 2 bullet points here. Now, do you see that what these 2 bullet points here are telling us is that first bullet point is telling us what happens with the statement itself. In other words, without the do and the OD. Okay? So what it's telling us is this. It's telling us we have the Hoare triple P and B, and then we have S, and then we have P. Right? Now, see, this S is the statement within the do loop, within the do statement. That's the statement inside, inside the guard. This is a statement inside. This P is an invariant, right? Because this P, like we discussed before, this P is invariant. It's true. It is a conjunct. It's part of a conjunct, and it's true here, and it's true here. So this P is an invariant, and this B is the guard, and there's no do in here, right? Now, the second bullet point is just a formal way of stating that the loop executes, that the loop terminates. So I'm going to write this as and loop terminates. And the fundamental invariance theorem says, suppose this, then something else. So it's in the form of an implication. Are you with me? So basically what it's saying is, suppose this is true. What does that imply? That implies this, P, but now the P is outside the do loop. So it's P, do, if B then S, or guard B, statement S, OD, in do. And now what we have is this interesting post condition, P and not B. So look what's going on here. This is a statement, this is a requirement, or this antecedent is talking about what's true inside the do loop. See, if this is true inside the do loop, but here, this precondition and this postcondition is around the statement without the do. This precondition and this postcondition are the precondition and postcondition of the Hoare triple outside the do. Do you see what I mean? See, there's a do and an OD here. There's not a do and an OD here. Here, this is just around the statement. Here, this is around here. So the main point of this is that this whole thing is inside the do statement. But this P, this precondition and this postcondition, these are outside the do, because the do and the OD is here. Whereas here it's just S. It's not do and OD and no guard here. Here, okay, so our observations, this is outside the do statement. Now, why do you suppose, and I'm not going to take the time to prove this formally. I mean, but you can see, I think you should be able to see why this is, I think we should be able to see why this is true. Because look, how did we say this do statement executed? It keeps doing its thing, and then what happens? And then how do we ever quit? What has to happen? How did we quit that do statement when we trace through it? How did we quit? How do you ever quit a do statement? How do you ever terminate a do statement?
When whatever you say while
Yeah, what's that called? While the what? That's called the guard.
the guard.
Yeah. Okay. Yes, it's because you terminate when the guard is false. Yeah. So you see, that's why. So what this is saying is that if P is an invariant of this statement, so if it's true both before and after, right? So therefore, if you have P and B, but of course this statement only executes if the guard is true, right? So if you start with P and B, then what's going to happen is this statement is going to execute. And then if P is invariant, and furthermore, if eventually the loop terminates, what's going to happen is the Hoare triple that's going to be valid is the invariant here, and then with the do and the OD here, and it's going to be the same invariant here, but it's going to be and not B, because that's what's going to be the case when you terminate. Yeah? That is the meaning of the fundamental invariance theorem, and I wish I had time to go prove it. But I think you can see why there's a base case and an inductive case, and it's you should be able to convince yourself that this is true. Now, so that's the fundamental invariance theorem, and we have here now a checklist. So P.30 is a proof method for do. So in the same way that with an if statement, the same way that when we had an if statement, we had a checklist, and we said to prove an if statement is true, we had A, B, C, D, we had that little checklist. Well, here's the checklist for the do statement. And it's based on this fundamental invariance theorem. And so here's the checklist. Okay? First of all, what we have to do is we have to prove, and actually, let's take a look at the shape of this program that we are trying to be able to prove correct. It says to prove, now look, there is not just a P here, there is a Q and a P and an R, right? Because typically what happens is, before you execute the loop the first time, you initialize, you set the state, and you initialize the state to make the invariant true the first time. And remember, in the example that we did, that initialization was what was that first statement before we entered the do loop? Oh, that was the guard. But what did we do before we actually got to the do loop? Do you remember? It was on this board right here. Yeah, it was x comma I gets 0 comma 0, right? So that was the initialization. So typically the way you write, when you write a loop, you initialize some variables, and what that initialization, the purpose of the initialization is to get the invariant to be true the first time. Okay? So now what we're going to have, so in general, our loops, whenever we prove our loops are correct, the way our loops are written is we have some initialization. So Q is the precondition before the initialization. Then we have a semicolon. And then after the initialization comes the loop invariant P. And then we have do. And then B arrow S, in do, postcondition R. So that's going to be the kind. And we'll do an example of this checklist. And you'll see what the initialization and the P and the guarded command is. So anyway, if we have this, then what is our checklist? A. First you have to prove that P is true before you execute the loop. So what do you have to prove there? Hoare triple, Q initialization P. Right? Is that good? Okay. Second, you have to prove that P is a loop invariant. So what you prove there is P and B, S, P. Okay, so what that's doing is that's doing this part, right? Are you with me? And then what has to happen is you have to prove what? Now look down here. You have to prove what? That the what? That the loop terminates. Okay? Are you with me? So here you have to prove that the loop terminates. And then the last thing that you have to prove is that R holds on upon termination. In other words, you have to show that P and not B implies R. Okay? And this follows from, and because what is R? R is the postcondition, right? So you have to show that P and not B implies R. And where does that P and not B come from? It comes from here. Okay? So if this implies the actual postcondition, then we've got it. All right? So all of that is, so this checklist is based on the fundamental invariance theorem. Okay, well, enough theory. Now let's go ahead and do an example. The example that we're going to do is the multiplication algorithm. And it's in the book. The algorithm is given in the book. It's 12.42. Now in the book, he doesn't tell us what the types are. But we know that the types I and P are integers. And this is the multiplication algorithm. So what does it say in the beginning? The precondition is Q. It's identified as Q. And that is 0 is less than or equal to n. The initialization is IP gets 0, 0. And then also X, and then the loop invariant P is 0 is less than or equal to I is less than or equal to n, and P equals I times X. Little p equals I times X. So in the beginning, of course, P is going to be 0. And then each time we go through the loop, what do? It's do I, so the guard is what? I is not equal to n. Okay, so we assume that, yeah, unfortunately he doesn't document what n and x are. So here we assume that x and n have some initial values, and in the end, we're calculating p to be n times x. So here, let's make a little note. 12.42, multiplication algorithm. 12.42, multiplication algorithm. We assume that x and n, have initial values. And we also assume that n is greater than or equal to 0. So x could be negative if you want. And the algorithm computes the product, x times n. The algorithm computes the product, x times n. So it's not too clear just by looking at the code that that's what it does. Anyway. All right, but it computes the product by adding successively. You can kind of tell what it does, because as long as I is not equal to, I starts off to be 0, and as long as I is not equal to n, what does it do? It increases I by 1, and it does what? Adds x to p. So by successive addition, it multiplies. So I think you can see. But now the point is, how do we actually prove this using the checklist? Okay, here we go. So prove using the checklist.
Like, is it better to initialize any values that you call like int x equals 0 first?
No. X, you can't. Well, we assume that x has been given. We assume that x has been given a value before this. I mean, like it could be an input. Like maybe you get this from maybe if it's like a calculator program, you get this from the, from what the user entered.
I don't think it matters what value.
X, yeah, there are no restrictions on x. X could be positive, it could be negative. Actually, in this example, x could even be a double. It could be a real number. Okay. But we assume that actually, but we do assume that n is an integer. because I and n, because I goes up by 1. So anyway, so let's prove using the checklist. What was the checklist? Checklist P.30. Okay. Using checklist P.30. All right? Well, what was our checklist P.30? Okay, so now you tell me. We'll take turns. We'll go around. So what's the first thing that we have to, so what was checklist A? You have your, so what do we have to do? Something implies something. What was it? Do you have it? We have to keep switching back and forth here. Okay, so what was checklist A? It's Q, we have to prove the Hor triple Q initialization P, right? Are you with me? So what do we have to, so what's the Hor triple that we have to prove? It's this one, and then this is the initialization, and then this, right? Are you with me? So how do you prove that Hor triple? How do you prove the Hor triple? Prove 0 is less than or equal to n implies what? Yeah, yes. WP dot what? IP gets 0, 0 dot P, right? That P is an that abbreviation, yeah? Are we good? So how do we do this? We assume the conjuncts, right? So how do we? So what do we do? We start with this, right? So we do WP dot IP gets 0, 0 P dot P equals by what's our old friend? Yes. P18 and textual substitution. What? So we got to look at this P, and everywhere there's a what? An I. So what does this turn out to be?
0 less than equal I.
No, yeah, but what? Yeah, 0 less than or equal to 0
Less than equal n.
equals to n. And
0 equals 0 minus 6.
yes. All right. So this equals by conjunctive meaning and math. Okay, so math and conjunctive meaning. Because what does it mean? 0 is less than or equal to 0 is less than or equal to n. What does that mean? 0 is less than or equal to 0. What is the conjunctive meaning of 0 is less than or equal to 0 is less than and yeah, and 0 is less than or equal to n. So that's this one. And yeah, and but 0 times x is math. I mean the and 0 equals 0, right? Okay. So this equals by, well, identity of and is, this is true, 0 equals 0 is true. Identity of and is true, right? Okay. And what about 0 less than or equal to 0? Yeah, so math, we know from math that 0 is less than or equal to 0, equivalence true. And we know that 0 equals 0, equivalence true. And we know that the identity of and is true, right? Identity of and. So this whole thing turns out to be what? So this is true, this is true. This whole thing turns out to be what? What's left after we? Yeah, 0 less than or equal to n. But now what do we do? Yeah, assume that's what the conjunct. So assume conjunct here. So here we assume conjunct 0 less than or equal to n, and so that's true. Boom. Are we good? Is everybody clear on that? All right, what about checklist B? Over here. Over here on this side. Okay, so what about checklist B? What do we have to do? What is it? What? Here, maybe we should look at this. So what was checklist B? What does it say? P is a loop invariant, right? So we have to prove P and B, S, P. So what is that in this case? So now what do we have to do? Prove what? P and B implies what? Everybody, are you with me? Implies what? What was it again? We have a little hesitation here, I see. So what do we have to do? We have to do P. We have to do the P here. This one that we just proved true, the invariant, and B, and then we put the statement without the do, right? And then we put P, right? So what does that turn out to be? So P implies the weakest precondition. Dot. Now what goes here? Yes. Oh, no. Yeah. IP, yeah, correct. IP, little p,
I plus 1.
gets I plus 1 p plus x dot what?
P equals n times x. I mean,
Well, the big P, right? Is everybody, are you with me on this? Okay. So let's do it. And obviously what we're going to do is assume the conjuncts, right? Okay, so let's do the weakest precondition calculation. WP dot I comma P gets I plus 1 comma P plus X dot P. So this equals by P.18 and textual substitution. So now, what was our big P? It's that, yeah? So what is that? So what do we get? P, everywhere there's an I, replace it with I plus 1. Everywhere there's an X, everywhere there's a little p, replace it by P plus X. So can you read off what it is?
0 is less than or equal
To
I plus 1.
I plus 1, right?
Less than or equal to n.
Less than or equal to n. And
P plus x equals I times x.
P plus X equals I plus 1 times X. Is everybody good with that? So here we have math and conjunctive meaning. Are we good? Math and conjunctive meaning. Now, so what's the conjunctive meaning of this?
0 less than or equal to I plus 1.
0 less than or equal to I plus 1 and
I plus 1 less than or equal to
I plus 1 less than or equal to n. And now can we do some math on this? What is I plus 1 times x? I times x plus x. So we have a p plus x equals I times x plus x. So what can we do to both sides? Yeah, p equals I times x. Is everybody good on that? We did a little algebra there. Okay, are we good? Distribute that. Okay. And now but now what can we assume? What conjunct can we assume? Because this p is all of this, is all of that. So which conjunct can we assume? Look at this. Which conjunct can we assume? This one, right? Notice that you can assume just one of the conjuncts.
And you can just set true.
Yeah. So this equals by assume conjunct. Assume conjunct P equals I times X, because that's one of the conjuncts of the P. So that means this is true. Well, true and anything is, okay, true is the identity for and, right? So this drops off, right? So basically what we have then is, now what's another way of writing this? 0 less than or equal to I plus 1. Let's take the 1 to the other side, and that becomes what? Negative 1 is less than or equal to I, and I plus 1 is less than or equal to n. Right? So now what conjunct can we assume? What's in? Now what conjunct can we assume that will help us here? That will help us get rid of this? What's one of the conjuncts we can assume? 0 is less than or equal to I, right? That's one of the conjuncts. So assume conjunct 0 is less than or equal to I. Okay, now look. If we assume this, if we assume that I is greater than or equal to 0, what do we know is also true? I is greater than or equal to -1. So we know this is true. If we assume this, we know this is true. Are you with me? And so this one drops out because we have an n. So basically what we have here then is I plus 1 is less than or equal to n. Right? Now what conjunct can we assume? Yes. Assume conjunct. Assume conjuncts I is less than or equal to n. That's one of the conjuncts. I is less than or equal to n.
But that's I plus 1.
Yeah, I know. So not only are we going to assume conjuncts I is less than or equal to n, we're also going to assume conjunct what? It's there. You can find it. Because what's the other conjunct that we have here? What's the other conjunct that we have here? We have what conjunct? See, not only do we have all of P, it's and B. What's B? What is B? B is the what? No, what does B stand for? The what? It is the guard. B is the guard. What's the guard? Yeah. And I is not equal to n. Does everybody see where this comes? This comes from the guard. Are you with me? Well, yeah, but you see it's P and B. It's not just P, it's P and B. So the guard, yeah, that's crucial. So the guard is I not, are you with me? But so if we assume I is less than or equal to n and I is not equal to n, then we know that this is what? True, right? By math. So this is true. Boom. Now, what is the, well, shucks. Shall we try to finish? Is there another class in here? On Tuesday? Are they waiting outside? Can you check, see if somebody's waiting outside? Because I would like to finish this. I would like to take an extra 5 minutes and finish this. Okay, let's finish this. I would like to finish. I would like to take 5 minutes. If you need to leave, fine. You can see it on the video. Okay. So the third thing we have to do is what? We have to prove that loop terminates. Okay. We have to prove that the loop terminates. Now, how do we prove? Now, this part is done done informally. Will this loop always terminate?
Yes.
Why is that? Why do you think it will? Because I starts off to be what?
Less than n.
Well, it starts off. I mean, it's set to what? Yeah. So I is initialized to 0. So here's the proof. I is initialized to 0. Okay, that's the first step point. And furthermore, what do we know about the value of n? It's greater than or equal to 0. So I cannot be greater than so it's initialized to 0. And so by Q, 0 less than or equal to n, I cannot be greater than n. It cannot start off being greater than n. By Q, this, I cannot be greater than n. Right? Now, each time, what happens each time you go through the loop? What happens to I? Yes. Each time through the loop, I increases by 1. Are you with me? And what about n? Does n change at all? There's no assignment to n. And n does not change. Okay? So therefore, what do you know? So what must I eventually equal? So I must eventually equal n. So what will happen at that point? Yes, and I not equal to n will be true, sorry, will be false, and the loop will terminate. Okay? Now so that proves that the loop terminates. Now just one more, we have to do part D. What does it say? Remember what it said here? Let's switch. It says R holds on terminate. So what do you have to prove? P and not B implies R. So what is that? P and not B. So we'll have to prove what? P and not B implies, and what was our R?
P equals n times x.
Yes, the whole thing that we're trying to calculate. So now how do we prove that? Well, let's do this and assume the conjuncts of the antecedent, right? So let's start with P equals not, so we'll start with P equals n times x. This equals, and we will assume conjunct what? Well, what do we have to work with here? We have P and, we have a bunch of conjuncts in P, and we also have a not B. So what's one of the conjuncts we can assume? I think we could assume P equals IX, right? Isn't that one of the conjuncts? Okay, so assume conjunct P equals I times X. So what will this be? I times X equals what? N times X. So now what conjunct should we assume? Yes. Assume conjunct not B, which equivales what? Which equivales not I does not equal to N, right? Which is I equals N, right? Not I not equal to N is I equals N, right? So if I equals N, what do we have? Yeah, then we have N times X equals N times X. Equals by reflexivity. True. Boom, we're done. Okay, well, we went a little over, but that's all right.